Nicolas Boucher, PhD student in computer science at Cambridge University in England. Welcome to the Data Exchange podcast.
Ben, it's a pleasure to be here. Thank you for having me.
So, you are here today because you are the lead author in a very interesting new paper on NLP attacks, so adversarial attacks against NLP applications. But first of all, Nicholas, you're technically in computer security is your area. So what led you to adversarial ML? And in particular, is ML a fashionable area among computer security researchers?
Yeah, it's a really interesting question. When I think of computer security, I generally think of computer scientists that really work across a broad range of subdisciplines within the field. And I find it very interesting that a lot of computer science security experts seem to switch very often and go from one discipline to another. And I think that's very much the case for myself and the lab that I work in. We generally look for interesting problems in computer security, things where we think there might be some potential for exploitation and writing interesting papers and really go after what seems like it's the big shiny topic of the time. And right now, that is most certainly machine learning. I think, the entire discipline, the entire world is really looking at machine learning and the interesting advancements that are happening there. And well, for us security folks, that means it's ripe for attack, and we really enjoy seeing what we can break and how we can fix it.
So yeah, so in many ways, if software is eating the world, ML is eating software. So,
That's
so,
one way
so,
to put
ma-
it.
so many software systems will have ML. So naturally, computer security people should be involved. Now, computer security is, generally you can find them in areas like traditional software, web software. So, you know, intrusion detection systems, penetration testing. Generally, in terms of adversarial ML, what are the general types of attacks? So, what's a high level taxonomy
Yeah,
of attacks
absolutely.
in ML?
Well, it actually might be interesting to back up one level above that because adversarial machine learning is certainly one of the hot topics right now. But if we're talking about security in general, there's really kind of two different approaches to machine learning. There's using machine learning as a tool to try to improve or degrade the security of some particular system, and then there's attacking machine learning models themselves. And we're really talking about the latter right now. But in speaking to the former, there's all sorts of antivirus functionality software that uses various statistical and machine learning techniques to try to do in an automated fashion what in prior years may have taken
In fact, the
analysts just.
first killer application of ML is spam detection.
Absolutely,
Uh,
absolutely, and the real benefit here is once you've created a model, you have the ability to scale it in a way that is just very challenging for something that typically involves repeated human interaction, like labeling spam, for example. So, but diving into that other category, the adversarial machine learning category, it looks a little bit different depending on the type of machine learning models we're talking about. If we're talking about NLP, that is a distinct subclass of machine learning. If we're talking about computer vision or audio, these generally look a little bit different. But we could probably come up with some general taxonomies here. So adversarial examples are inputs to machine learning systems that cause them to do something different than what you would expect. And oftentimes we add somewhat artificial constraints, like the input to some machine learning system needs to look sufficiently similar to something that's not adversarial, that perhaps a user wouldn't notice that something evil might be going on under the hood. And there's all sorts of classic examples, perhaps one of the most iconic being images that have a pixel value or a small number of pixels that are ever so slightly modified. And it turns out that in certain computer vision models that aren't properly retrofitted to defend against these sorts of attacks, it may cause say, classification that seems entirely incorrect to a human, but to this model might seem to be perfectly legitimate. Now, it turns out you can do this beyond just computer vision. If you move into the audio domain, there's been some very interesting recent work on audio signals that are poisoned, where you have some small amount of information that is either not or barely perceptible to humans that will, for example, cause speech to text to output something very different than what a human might expect when they're listening. And just recently, my group has been looking into natural language processing, specifically into text-based machine learning models, and I imagine that's the topic we'll dive deeper into today.
So in my mind, so there's the attack of the type of attack where you cause a model to do something that it's not supposed to do. And then there's this other set of attacks that are kind of like the model extraction, model replication kind of attacks, where you kind of either steal data or still steal the model or both. So in general, so you've got the attacks where you get the model to misbehave, and then you have an attack where you steal something. Before we get into the NLP stuff, so generally in ML and security, how prevalent are these? Because are these like basically mostly theoretical things, or has there ever been really a case of model replication or model extraction?
Yeah, those sorts of questions can be very challenging to answer because I think the reality is that if there is a sufficiently motivated adversary, depending on their goals, they might not choose to speak broadly about what they've been able to accomplish. But when we look through the academic literature, we can see that inference to see what data points may have been used to train a model, or model extraction, forms of transfer learning that might be able to extract model weights without direct access to those weights. These are things that we've seen the academic community say, yes, we can do these things, and there are defenses that you can put in place to make it more challenging. But is it theoretically possible? Absolutely. And the security person in me says that, well, if it's theoretically possible, it probably means there's someone out there doing it. And once we get to talking about the NLP work, I can give some very tangible examples of ways that this might be abused, and that I suspect if we were able to access enough information, we would see that it was.
Yeah, in cybersecurity, so information security increasingly seems like it is becoming like, it's basically data security, right? So companies need to secure their data because data privacy is such a big thing. There you can see attacks, real world attacks. So companies need to invest. But in ML, Nicolas, if I'm just starting out in ML, why should I bother to QA my system or secure my system when I'm barely at the point where I'm deploying models, right? So what's the argument for putting your security hat earlier on?
Yeah, this is one of the big questions that I think has led to some real challenges in deployed live systems, because the argument is very compelling to say, I just want to make my model as performant as possible. I'll worry about these other concerns when I get to the point of rolling out some production system, or if I'm a large tech company, maybe I approach these problems relatively differently. But what that leads to is a culture in the machine learning community that's worried only about performance. And right. If these people that are trying to maximize performance at all possible costs are the same people that are building production models that are deployed by either big tech companies or startups or governments, they're going to think the same way as they're building those production models as when we're experimenting and trying to make the most performant systems. And I think one of the things that we've seen in this bad characters paper is that it's actually much easier to defend a system if you're thinking of security and you're thinking of attacks as you design models initially. It's much harder to retrofit that onto existing models, at least in some cases. So you should be motivated to think about this earlier on, because if you believe that the system that you're designing is going to have real world impact, it's going to save you time when you get to deploying that model.
Yeah, this is the whole kind of responsible AI, right? So
certainly,
right. So and then so in web security or traditional software, you have contests like capture the flag kind of things, right? So in ML, it's like you said, it's all about benchmarks. Maybe we should have it NeurIPS or at ICML like a capture the flag for ML models.
I love that idea. And I think that as machine learning as a discipline grows and there's more and more people and more conferences, I think we're going to start seeing things like that maybe are signs of a maturing discipline, of these different subgroups that develop, and people who are beginning to specialize in, say, machine learning security rather than just security itself with an interest in machine learning. So I'm fully behind you on that one.
So, what led you to NLP models in particular?
Yeah, this is one of those papers that really came together by coincidence. It started with a conversation I was having with another of the future authors on the paper, and we were talking about how challenging it can be for multilingual speakers to type their language if those languages, for example, don't use the same set of characters, maybe Latin characters in the case of English. And we started saying, gosh, yeah, it's awfully funny to think about that, but these different characters, they're encoded differently, and sometimes you may just choose to type the thing that looks the most similar in English to the language that you're ultimately writing in, because you don't want to switch modes on your keyboard or switch over to your other keyboard or something like this. And there was this little moment that sparked in our heads and said, wait a minute, natural language processing, the whole area of machine learning models that take text as input, they really assume that text is going to look in a certain way. And any time that there is some sort of very key assumption to how a system operates, that's when us security people start to get really excited. And we started to say, well, I wonder if there's a way that we could exploit that. And we start reading, and we realize that there's potentially a really ripe area for attack for text that doesn't look poisoned, but potentially does something very adversarial when you use it against a system.
So before we go into the specific attacks, so I guess we should go into the specific attacks for you to explain some real world examples, right? So
yeah, certainly. So in the bad characters paper, which is what we're here to discuss today, what we find is that we can create inputs, adversarial examples, to machine learning systems in the natural language processing domain that are just text, but they look like standard text, but they contain invisible things inside of them that cause the model to do something that you don't expect, just as we were talking about earlier.
So Nicolas, just to make it concrete, because a lot of applications use the keyboard as an input mechanism, right?
Mm-hmm.
So are we talking about, what class of applications are we talking about? Anything that uses a keyboard, like search engines, forms, web forms?
Yeah,
or is it specific to what you started out with, which is much more kind of that multilingual machine translation example?
Well, it ended up being much broader than what we started with. So our claim is that any undefended model, undefended for this particular technique, that processes text as input, is likely vulnerable to this attack. So you could say if you were able to use a keyboard to interact with some machine learning model, chances are this is going to be a valid technique.
Where keyboard broadly defined includes smartphones even, right?
Oh, certainly. Anything that's going to generate text of some kind. And there are so many ways that could ultimately be generated. And this is, at its core, it's a hack, a trick that we came up with about how to encode text in a way that just really causes machine learning models to break.
So you have 4 basic categories. So invisible characters, homoglyphs, reorderings, and deletions. So let's go through each of these examples.
Yeah, well, that works great because the first one is probably the easiest to grasp and I think really illustrates the entire series of attacks. So when you consider machine learning models, typically the first, specifically natural language processing models, usually the first stage is to take text and to tokenize it and to run it through a dictionary that will take that text input and it will change it into a set of vectors, a set of embeddings that will ultimately be the raw input that's consumed by that model. Now, It turns out that dictionaries often have the limitation that if there's something it hasn't seen before, it doesn't know what to do with it. So it gives it an unknown token to say, here's something that I don't know what it is. There's been some interesting advancements in the
So,
field to
so
try and.
isn't the program supposed to break if it's like a character outside of the Unicode spec, then you get an error message.
Well, that's an interesting point, and if it's outside of the Unicode specification, then quite possibly, depending on the implementation. But the takeaway here is that most dictionaries are not comprehensive. They don't cover the entire Unicode specification. They cover only the characters that would have been seen during training time, or at least the formation of that particular dictionary. So speaking of Unicode, Unicode is a vast specification. It contains just many tens of thousands of different characters, and many of these characters look very similar, which is what will ultimately lead to this attack. But if I've trained a model that has only seen text that is, say, in English, there's a pretty limited number of characters. It's going to be the Latin alphabet, maybe some punctuation, maybe a handful of other characters involving accents or other languages that may have been quoted. But the portion of the Unicode specification that would have been seen at training time is almost always a very small percentage of the entire specification. And what we're trying to do is to use characters that weren't seen during training time, that aren't included in the dictionary. And in this case, as long as it is valid Unicode, in almost all cases, the model isn't going to break or halt. It's just going to give an unknown token.
So let's say I have a form, and
Mm-hmm.
behind the model is a form. So
Mm-hmm.
how would you attack me? I mean, how? Because you don't know what I use for training. You don't have access to my training data, right? So
Yes, you're absolutely right. So what we found is that in the cases where you don't have access to model weights and you don't know what dictionary is being used, you're actually not at as big of a disadvantage as you may think. And this enters into the class of genetic algorithms that are often used for gradient-free optimization, techniques that are used to create adversarial examples without access to model weights. And these things sound a lot more complicated than they actually are. Under the hood, what they're doing is they're trying a whole bunch of different inputs that it thinks may cause a problem in some models, and it's seeing which of those cause the biggest problem,
but
and
then,
then
but then,
it's
but then
optimizing.
I put logic in my form so that after 4 tries, you're done.
Absolutely. But in this case, I now use a botnet that has maybe a
Oh,
million
I see.
different clients that are spread everywhere to attack the model. Or perhaps I create something that spins up virtual machines in a cloud environment on demand, makes a few requests, and then goes through a different IP address. It's actually much harder to rate limit clients than you may expect.
Yeah. Of course, you security guys always have an answer, right?
Well, and that's one of the challenges is a
And
motivated
by the way,
adversary.
ML people don't think this way. That's the other problem, right? So that's why actually inside ML teams it might be good to have people with security backgrounds, right?
Well, that I think is the ultimate goal of what we're pushing towards, and I do think that is where the field is going to mature into. Just in the same way that all of these other disparate domains, whether it's general software engineering or whether it's writing compilers or something like this, there's now oftentimes the security person on the team or a whole team of security people that are trying to call out some of these abusive adversarial things early on in the design process.
So invisible characters basically have to do with the fact that you try to find characters that are not seen in training but close to what is seen during training, right?
Well, it's actually a little more subtle than that. That's perhaps a little closer to one of the later categories. So it turns out that in the Unicode specification, that is the specification the majority of the world uses to encode text, there are all sorts of characters that don't render to anything. They're actually invisible. It's a character that goes into a document, but it doesn't generate any glyph when it's rendered by the machine. And there's all sorts of reasons for this. Many of them are specific to formatting. However, it turns out that oftentimes these formatting characters only work in certain settings. So if I have a formatting character that's only used in the ancient script of linear B, and I drop that into some English, Latin character text, it will have no effect. And what this means is that as an adversary, you could inject these invisible characters that generate no visible sign as often as you want, wherever you want, into text. And it also happens that because these characters rarely appear in the wild, they're often not in training data sets. And this means that I, as an attacker, can say, all right, if I have a dozen different characters that generate no visible glyph, that's my sample size. That's what I could potentially inject into some adversarial input. And then I just try putting these invisible characters spread across the input, and then I run that input through the model. And if it generates something that is different than what I would expect, that then becomes an attack vector.
So then, did you folks kind of create like test harnesses or testing tools that can be pointed to someone's NLP application?
Somewhat. So we wrote a whole bunch of different scripts that test various different models, and we made all of those scripts available. Anyone could go in and drop their personal model, the model that they're interested in, into this set of tools and evaluate if our techniques will work against their models. It's a little bit more effort than just giving a URL to some model and getting a response back. But I would say
if you were to think ahead 3 years from now, it's conceivable that someone would have access to tools like this.
Absolutely. In fact, actually, we did publish a website with our paper that has some general testing tools just built into a web browser. And what this will do is it will generate random potential adversarial examples. And you could take a whole bunch of these and drop them into your model. And if you find that your performance degrades exceptionally, significantly, then it's very, very likely that your model is vulnerable to these attacks.
So this invisible character attack, Nicolas, is this? Mm-hmm. So the goal here is for you to do what? To make the model misbehave or what?
Yeah. So one very tangible example, and I'll probably circle back to this one multiple times, but social media platforms or comments fields on blogs or websites or things like this, they allow users to put freeform text that's published out to the world. And there's a strong incentive for the platforms that host this content to make sure that there's not abusive content that's being put. It could be any number of things, but let's say that it's a threat of violence, for example. So there are lots of often called toxic model detection models that are created, and toxic content detection models, and these are used to block that content without the need for a human to go in and review that particular, say, tweet or Facebook post or WordPress comment. So if you wanted to evade that sort of mechanism, if you wanted to be able to post toxic content without being blocked in an automated fashion, you could very likely put invisible characters inside of your text. And as long as the model that does that toxic content detection is vulnerable to this attack, there's a very high chance that it won't pick up on your threats or your violence as being what it is.
Huh, interesting. But then, can I, if I'm another reader, I won't be able to read it either?
Well, you will, actually, and that's the interesting part. So what we're doing is we're exploiting the difference between how a machine learning model sees text and how a human will see text. Or to be more specific, we're attacking the divergence from the rendering pipeline and the logically encoded pipeline for Unicode text. And in this particular sense, if it's an invisible character, if I put an invisible character into text, it may cause the toxic content detection model to fail. But you won't see those invisible characters as a human. So when that text is rendered, you'll still see what I want you to see.
Huh. Very, very elegant. So what are some of the other ones that scare you? What are some of the other NLP attacks in your paper that scare you?
Yeah, well, maybe just very quickly going through those
Yeah.
other three attacks because they're all the same idea, just with a slightly different execution. The second category of attacks we describe are homoglyph attacks, and these are actually perhaps the easiest to imagine. There are characters in different linguistic families that look very similar. So, for example, Russian speakers use the Cyrillic alphabet,
Hmm.
and any speakers of Russian will tell you that there are lots of Cyrillic characters that look very similar to the Latin characters that we use in English. And there's lots of historical reasons for that I'm sure linguists would be able to tell you much more about than myself. But what this means for Unicode is that if I take, for example, the X character, X in English, there is a Russian character that looks virtually identical, that is identical in most fonts, and I could just swap those two characters. And if indeed the model that I'm attacking has never seen a Cyrillic X before, well, it's going to be encoded as one of these unknown tokens, and it's going to have the exact same effect as these invisible characters. And what is most insidious about these homoglyph attacks, as we call them, is that they are incredibly hard to defend against. And it at first seems very simple. Well, why don't you just get rid of all characters that aren't being used by the language that you expect? But this becomes really hard because when you have internationalized applications that have users from many different countries and many different languages, it is very challenging to constrain their input. You may find that you, say, make it impossible for users of a specific language to interact with your application.
So I see. So the model won't be able to see a bunch of these characters. So then the model will say, "Huh, this is not hate speech." But then when it renders, it looks like hate speech to the reader.
That's exactly it.
Right.
Now, the third technique we call the reordering technique, and this one is probably the most complicated, but I would dare say it is by far the most interesting. And to describe this, Unicode and most other text specifications have support for both left to right languages like English and right to left languages like Arabic and Hebrew. And if you are going to support both left to right and right to left text, you have to come up with a deterministic way for those two character sets to coexist. So if I, for example, as an English writer, decide to quote something in Arabic inside of my writing, I need to.
Which, by the way, for our listeners, Nicholas, people who speak multiple languages do that all the time. They go back and
All the
forth
time.
as they're speaking, right? So
All the time. And these things that sound like they're edge cases, like, for example, saying something, writing something in English and quoting something in Hebrew, which quotes something else in English, which contains Arabic numerals. Like, this sort of stuff happens way more often than you might expect, which is just a consequence of the modern global world that we live in. It's to be expected. And to support these scenarios, there's something called the bidirectional algorithm, at least in the case of Unicode, and it enables you to mix right to left and left to right text. But the challenge is that sometimes that algorithm won't put characters in the order that you want. Maybe you actually do want to display.
so wait a minute. So as a developer, I'm relying on this algorithm. I'm not.
Yes.
I mean, that's beyond my pay grade. I'm just a developer. I'm going to rely on this algorithm. So it seems like
Absolutely.
it's like an infrastructure problem that someone has to
Yes.
fix, right? So
Yes, and actually that algorithm, it's part of the text rendering pipeline, and that pipeline is very rarely implemented at the application level. It's typically implemented one level below that, maybe in the operating system, or in the case of web browsers, it's often implemented in the browser itself as opposed to, say, in some web page that loads within that browser. But and where it gets very insidious is this: the designers of this algorithm correctly said that sometimes you want characters to display in a different order than it might assume. So, for example, if I am an English speaker who is trying to teach Arabic to someone, I may actually want Arabic characters to be displayed left to right for the purpose of instruction. And in this case, I need some deterministic way to say, change the order of these characters in a way that you don't expect. So they created these things called bidirectionality control characters that allow you to override the display order of text. And this is exactly what we exploit in the reordering attack. So what we do is if I have some string, A, B, C, I can take which is normally displayed left to right. I can put in one of these control characters to say turn on right to left mode instead of left to right. So now, even though it's encoded right to left, A, B, C, when it's rendered, what I see is C, B, A. And then in our attack, what we do is we say for every reordering that we inject, we reverse the characters to counteract that reordering. So if I want to display the string A, B, C, what I do is I say right to left override C, B, A in the encoded order. But when you look at this, it just says A, B, C. You don't realize that it's actually backwards at the encoding level. But guess what? The machine learning model that this text is being injected into, it does see the logically encoded order. So it sees it as CBA, even though you see it as ABC. And in the paper, we present an algorithm that can be used to create these reorderings of characters. But what we find is that there are virtually limitless, but specifically an exponential number of different reorderings of any particular string of text relative to the length of the text.
And then the last attack is deletion.
Deletions, which is very straightforward. You're very familiar with the backspace character on your keyboard. That backspace character, that key, it generates a control character that says, please remove the previous token that was created on this line of text. In many settings, not all settings, but in many settings, we can just manually inject that backspace character, and it will cause the character before it not to display. So if I can control the encoding of text, I can inject arbitrary things that say whatever I want and then follow it by a whole bunch of backspace control characters. And even though you won't see those deleted characters when they're rendered, the machine learning model will. And this is exceptionally powerful in, say, attacks against a machine translation, because I could, for example, put a whole bunch of specific words, full words that are not perturbed in any way, into some string, and then a whole bunch of backspace characters that remove them so you don't see them. But then when the translation model processes, it does see those things, and it will output the text that was hidden from you in whatever the target language is.
Wow. So to what extent should NLP teams be worried about these things today? So is this more of a concern a year or two from now?
Yeah, these attacks are actually really easy to perform in practice. And we talked about, say, an invisible character. You could just Google zero width space right now, which is a canonical invisible character, and you could copy it to your keyboard, and you could go paste it into the input field of some machine learning model. In fact, I encourage anyone who's listening to give that a try. You may find that that model just gives you some garbage output that is not at all what you're expecting. That is an exceptionally easy attack to implement. And similarly, you could drop in Cyrillic X's where Latin X's are expected. And the bottom line is that if you want to cause a model to fall apart and it takes text as input, if there's no defenses in place, you can go attack it today. So how concerned should machine learning architects be about these attacks? Well, it depends how concerned you are about the security of the model. If you're talking about some local model that sits on a computer in an isolated environment and doesn't affect anyone anywhere, then great, you can probably deal with lower performance in an adversarial setting.
Well, for example, in NLP in particular, there are many verticals and domains where text is very important, right? So healthcare, doctor notes, and
Absolutely.
things like that. In finance, things that can move markets. Right, so chat boards, earnings reports, news stories, right? So things like that, right?
Absolutely. And actually, finance is an interesting area to pick up on, because that reordering attack that I was discussing previously, if I simply take some financial earnings and I change the order, say reverse the order of the numbers and the bottom line of some spreadsheet, and then I put in a right to left character, if there is some automated trading system that is reading that, well, guess what? It's going to see the reverse of the characters.
Yeah, it doesn't, and it doesn't have to be a big deal. It could be from 2.51 cents earnings per share to it becomes 2 $2.15 from $2.51, right? So
You could make it say virtually whatever you want if you combine all of these different techniques. And there's all sorts of questions. What does that look like in a legal setting? Is that genuinely adversarial, or is this just a trick some people use to try and mess up automated systems? Are you moving markets as an adversary, or are you just a clever investor? I don't know. But these things could certainly be used in practice right now.
so generally, for responsible AI, my advice to teams and our listeners is there's a couple of things you can do today. The first one is improve your documentation. So document everything, data, models, and all sorts of, and everything related to them, and also improve your basically your testing and validation, which is pertinent to what we're talking about today. So one thing that I want to bring up, Nicholas, is we are also in the age of black boxes, right? So transformers, large language models. So these models are getting harder and harder to build. And in fact, most developers probably just take a lot of models off the shelf and do some tuning and transfer learning. Um, so many of them may not actually know the details of how the model works. They may have control over how to tune the model for their particular domain. Because a lot of these models, while they're good, you're not going to be able to use them off the shelf necessarily. So imagine a named entity recognition model that you take off the shelf. Well, if you're in some obscure area in healthcare, you'll have to tune it somewhat, right? So you'll have some knowledge about how the final model got deployed, but you may not know the entire architecture of the model, right? So to what extent then are you worried that we are in this kind of black box era?
Well, I think the problem that you're describing actually generalizes beyond machine learning. And the way that I like to think about this is there are lots of developers out there that know how to write code in Python. There's lots of developers that know how to write code in JavaScript. But it doesn't mean that they know how those bits of code are translated to
Oh
machine
my God.
instructions.
I mean, the Python ecosystem,
Yeah,
I mean, there's so many potential sources of failure there with pip and
sure. Sure.
So each library depends on 20 other libraries, right?
Absolutely. Well, the supply chain implications of modern infrastructure is certainly an area of discussion in and of itself. But you think of the average enterprise developer these days, and ask them to explain to you how two numbers are added at the machine instruction level, or even crazier at the electrical engineering level. How are transistors used to implement this? And I would venture to say there are probably not that many people that could describe exactly what's going on when you start with interpreted Python code. But that doesn't mean that those people
No,
aren't able to leverage the tool.
there's a difference between linear regression and some real, where you kind of know what's going on.
True.
So,
That is very true. Although one of the things about the security domain is it really only takes one small assumption that is incorrect for you to be able to potentially have something large fall over. So as an example, I've come across some very
I
interesting.
like how security people think, by the way, because basically, oh, here's a system. How do we break it? Basically,
It's exactly it. It's exactly it. But I came across some things recently, some amazing cryptographic work that was talking about these great properties of how you could build this huge system, actually using some homomorphic encryption and various different crypto techniques. And at the end of the day, the specification forgot to say whether the bytes were encoded in little endian order or big endian order, how those zeros and ones are actually written to the disk. And, well, guess what? The whole system became immediately unusable as soon as everyone went to implement it. These tiny little details, these assumptions can lead to massive vulnerabilities, and it becomes challenging. So I think on your previous topic of, what does this mean for the average machine learning engineer? Do they need to understand this stuff? I think the answer is it's good to know what's going on, but it's also impractical to expect that everyone is going to know every component in the pipeline.
Right. But also, as you alluded to, we're also entering an era where the way models get built will be different, right? So before
Yes.
you would build your own models, now maybe you're more reliant on someone else building
Sure.
a model and you doing some tuning, right? So
Sure.
yeah.
Absolutely.
So, but as you point out, this is not unique to ML. There's a supply chain problem in all of software.
And it's one of those things you have to not think about too much, because as soon as you do, you realize how fragile it is, and it can be a very scary world in that sense. But as you say, these are black box models. I challenge anyone to explain why the modern large language models work the way that they do, and why they're more effective than a model that's a little bit different. It's these things are practically indescribable. It's we found experimentally that they work, but it doesn't mean that we know what's going on.
Yeah. What is the in the future? What will be the log4j attack in ML? In ML, right? Yeah.
Actually, this is an interesting topic. So, one of the other co-authors on this bad characters paper had written a previous paper on something that they called sponge example attacks. And as a brief aside, it's very interesting. What they found is that certain inputs to machine learning systems can cause significantly longer inference time than other inputs, which on the surface doesn't sound like a particularly terrible thing. But what they found is that they could get many orders of magnitude longer inference time, and all of a sudden you begin to realize that if I have some text-based inputs that take a long time to compute, and I have a whole bunch of clients all send those at the same time to the same online model, well, what you've just done is you've created a denial of service attack, and
Right.
that model may just fall apart at the hardware level. So I think that those sort of things, the looking at the underlying hardware and, these high-level ideas, these matrices that are multiplied together, and these forms of backpropagation, how they're actually implemented, that systems level, there is going to be all sorts of opportunity to attack that level in the future, in my opinion.
So in closing, while I have you here, so another area that I'm interested in is this whole confidential computing
Hmm.
domain, which has many components, right? So there's
Mm-hmm.
homomorphic encryption, multi-party computation, differential privacy, secure enclaves, and so on and so forth.
Mm-hmm.
But so homomorphic encryption, um, basically the ability to do computation on data while it's encrypted.
Yes.
Great. We have systems out there. The impression I get is it's quite slow for ML. Maybe you can do inference, but even if you can do inference, it's all batch, and it's probably not deep learning. It's probably more like a regression model. So since I'm not paying attention to this closely, what is the state of the art as far as performance and practical usability of FHE?
Yeah, fully homomorphic encryption is absolutely fascinating. To me, it's one of the most interesting current advancements in cryptography, at least in the modern era. And as you point out, it's exceptionally computationally inefficient in most cases. So, when we talk about modern machine learning systems, we oftentimes care a lot about how long inference takes. And let's just throw aside training for a minute and just talk about inference. And if you have some live model that's deployed somewhere, if it's going to take twice as long to do inference, that actually could be a substantial cost for you to host that model. But when we talk about using homomorphic encryption of any kind to run inference, we're not talking about a 2 or a 3 or a 4 times increase in computation. We're talking about massive, massive overhead. So if you are in a domain where you can tolerate a absolutely massive amount of overhead for specific operations, fully homomorphic encryption is something that you should be considering. You should look at the techniques that are out there, and at the moment it's still very technical. There's different crypto systems, and you need to figure out which is most suited to the operations that you'll be performing. But yeah, absolutely, go ahead and consider that. But if you're talking about some kind of mission critical model where inference time matters, we're far too early to be talking about that.
There's no ASIC or specialized hardware in sight, right?
Well, not that I've seen. It doesn't mean that people aren't working on that, but I think at the moment it's specialized hardware might help, but just from a logical level, there is so much more computation that you need to do, even just to add two numbers together, which is something that we think of as such a straightforward premise that we don't even imagine the computational overhead. And if you're able to deal with limitations on the type of math that you can do, for example, if you say I want to be able to add numbers, but I don't need to be able to multiply numbers, or vice versa, you end up in this world of partially homomorphic encryption, and that is much more tenable. And in areas other than machine learning, we've already started to see that take root. As a very brief aside, the security of election systems. There's all sorts of absolutely fantastic proposals and projects that are going on how do you tally up election results in a way that everyone will believe while computing over ciphertext, so you never see how any one individual votes. There's this fantastic project that Microsoft is doing called Election Guard that, if you're interested, I highly recommend looking into. But the bottom line is partially homomorphic encryption, fantastic. Fully homomorphic encryption, fascinating, but we have a ways to go.
And the election topic is interesting. I won't go into it too much, but in the U.S., I think it'll take more than more than silence.
Well, you point out something interesting there, and that and this comes up in the security domain quite a lot. The security of a system is more than just the technical implementation of that system. You have to know who your users are and how they operate, because if you've used the best form of encryption that there is on the planet, and there's no way anyone could break it, but you convince someone to tell you the password, the system is no good. So there's a lot to consider.
Yeah, it seems like it always comes down to social engineering.
Yes. Absolutely. Absolutely. I mean, and if you are being realistic about the sorts of attacks that are probably having the most impact in 2022, I think social engineering, phishing, these targeted kind of attacks, like this is how people are gaining the keys to access systems and then do very large attacks. So there's a lot to consider in that area.
And with that, thank you, Nicolas. This fascinating tour through adversarial ML, specifically NLP, because NLP is such a hot topic. So many people working on NLP applications, but also on the research side, the models are getting better. So then there's even more and more. The number of applications is expanding as we speak.
Absolutely.
All right.